Welcome back, everyone, to this special edition of the Algebraic Graph Theory Seminar. Tonight, we have Gordon Royle, who's going to be speaking to us. And I'll get him to put up his slides now. Something to do with real roots of the chromatic polynomial, but I can read the exact title in a minute.
Okay. There you are.
Real chromatic roots. There we go. Gordon is going to tell us about real chromatic roots. So I will let him take it away.
Okay. Can everyone hear me, first of all? Yep. I keep dropping this pencil. Okay, so thanks very much for this opportunity to speak in the Waterloo Algebraic Graph Theory Seminar. Of course, this is very familiar to me. Waterloo is, has played a major role in my academic life. But for those of you who don't know me, where I am now is in Perth, Western Australia, which is which is this city here. So Perth is a city of about 2 million people. It's pretty much just a standard modern city. It's on the river. This is the Swan River you can see there. And it's also on the ocean. So it's where the Swan River meets the ocean. This, you can see I've marked on the slide here, the antipode of Waterloo. So you literally couldn't get further from Waterloo if you tried. If you went to Toronto Pearson Airport and said, I want a ticket to the furthest place with an international airport, then Perth would be it. So, because we're right on the sort of edge of the world, we're in some senses fairly isolated. That's sometimes a good thing, sometimes a bad thing. In the last year, it's been a very good thing because by closing the borders, we've kept COVID out completely. We only had one case in the last 10 months, except for those who were caught coming in with, from international locations with the virus. So as a result, everything is normal here. I teach face-to-face and we just do, go to concerts and events and cafes as one would normally do. There's the university. It's sort of a pretty place. I've been here for a very long time now. So what I'm going to talk to you, what I'm going to talk about today is the subject of real chromatic roots. And this is something that dates right back to my first time in Waterloo, when I arrived in 1988 as a postdoc with Ron Reed. And Ron Reed, who is a real amazing person, amazingly accomplished person, mathematically, musically, and in many other ways, he gave me two papers to read, one of which is called Limits of Zeros of Recursively Defined Polynomials, and the other is called Is the Four-Color Conjecture Almost False? And basically told me to get to it. So ever since then, I have periodically returned to studying chromatic roots of the roots of chromatic polynomials, and sometimes make a bit of progress, but there's always just as many questions open at the end of it as there were at the beginning. Sometimes the questions change, but that's about all. Okay, so with this audience, I don't really need to give much of an introduction as to what graphs and graph colorings are, but just to remind you, so a graph coloring is just an assignment of colors to the vertices where no edge has the same color at each end vertex. So there's a coloring of the Peterson graph. That is a proper coloring because the edges are all, any edge has sort of just got two different colors at each end. Okay, so the chromatic number, which again, probably everyone here already knows, is the smallest number of colors that you need to give a proper coloring of the graph. And the Peterson graph has got chromatic number 3 because there I've shown you a 3 coloring. You can check that each edge is okay. And there are obviously no 2 colorings, which means that the chromatic number is exactly 3. Okay, these, in 1912, Berkoff introduced the function, which we now call the chromatic polynomial, which just counts the numbers of proper q-colourings of G. So if q is a positive integer, then p sub g of q is just the number of ways of colouring the graph with a palette of q colours. Two colourings are distinct if they differ in any vertex. So we've got no concept here of, we're literally counting different q colourings with this particular palette of q colours. Okay, Berkoff introduced this because he was trying to solve the 4-colour conjecture. So he wanted to show that the chromatic polynomial of any planar graph, if you evaluated at 4, then you would get something that's non-zero. Now, obviously, counting things is perhaps harder than showing that they exist. But sometimes it's easier to solve a harder problem than it is to solve an easier problem. So Berkoff described these two ways as type 1 and type 2. So type 1 is where you just try to show combinatorially that there's a 4 coloring. Type 2 is when you actually count the 4 colorings. So one's qualitative, one's quantitative, I guess. Of course, as we know now, the only known proof of the 4-color theorem is combinatorial in nature. So we don't really know anything about the number of 4 colorings of a planar graph. Okay, Berkoff's 1912 paper is basically dedicated to showing that this function actually is a polynomial. And the familiar deletion-contraction relation says that if you have any edge in a graph, the chromatic polynomial can be expressed as the chromatic polynomials in terms of the chromatic polynomials of 2 smaller graphs, the graph obtained by deleting the edge E and the graph obtained by contracting the edge E. So contracting the edge means drawing its endpoints together, sort of sucking the points together until they form a single vertex. You lose the edge and you lose one vertex. This is, as far as we know, pretty much the only way that we can actually calculate chromatic polynomials for general graphs. So deletion contraction is obviously an exponential algorithm. So chromatic polynomials are hard to compute, both in practice and, of course, in theory. We can do, say, lots of nice things once we've got the deletion contraction relation. And the two main things are that it's a monic polynomial of degree n, and it has alternating coefficients. Okay, so each graph simply has a chromatic polynomial. There's an example. I've just drawn a graph. I've calculated its chromatic polynomial. I factored it, and then I've plotted it just in the normal sort of XY plot of a graph. We can then look at the real roots of this polynomial, and this graph happens to have them at 0, 1, 2, and some number around 2.3. Okay, so graph has a chromatic polynomial. A chromatic polynomial has roots, and that is what we're going to be studying. So way back in 1988, I was using one of the first computers around. I mean, I guess not first computers around, but I was using the computer at the University of Waterloo, and I calculated all the 9 vertex graphs, calculated their chromatic roots, but now their complex chromatic roots as well as their real chromatic roots. Like, because it's a polynomial, there's nothing to stop you viewing it as a polynomial over the complex numbers, or over the integers, or over the reals. So this is the pattern that I saw way back then. And basically the difficulty is try to explain that pattern. Why do the chromatic roots look like they do? So here is the fundamental question that sort of guides everything. What I want to do is find bounds on the location of chromatic roots in terms of parameters or properties of G, and in a fairly general sense. So I could say maybe the property would be planarity, and then I'd be asking for the chromatic roots of planar graphs. Or it can be a function of, say, the maximum degree of the graph. Can I say where the chromatic roots must lie if the maximum degree is below a certain value? Okay, it's been observed a few times that really the study of chromatic roots falls into three quite distinct sort of theories. There's a theory of integer roots. Well, integer roots is easy because if you have colors, if you have fewer colors in the chromatic number, then there are no colorings. And if you have at least as many colors of the chromatic number, then there are definitely some q-colourings. And so the integer roots basically are just all the integers from 0 up to the chromatic number -1. And that's that. The real roots behave slightly differently. And that's what I'm going to be talking about for the rest of the talk. And then the complex roots. Now that's sort of an interesting topic about which I've talked many times, including several times at Waterloo. So you might think that taking the complex roots is a bit of a strange, unmotivated thing to do, because what on earth do we care? It doesn't make any sense to talk about the number of 1 plus I colorings of a graph. But it turns out that, in fact, the complex roots are incredibly important because the chromatic polynomial is just a special case of the partition function of the Q-state Potts model. The Q-state Potts model is used to study phase transitions in various statistical physics models, and these phase transitions can only occur at the real limiting points of complex roots. So there's a vast literature in statistical physics calculating chromatic polynomials and their roots for lots and lots of families of graphs. Okay. Of course, any result for complex chromatic roots will apply for real chromatic roots, will specialize for real chromatic roots as well. So here are two results due to Alan Sokal. The first one says that there's no limits to where complex roots can go. In fact, chromatic roots are dense in the complex plane. If you take this graph here, which is the generalized theta graph 8,3, so that means there's 8 sort of path of length 8, and there are 3 of them. 1, 2, 3. Now, if you change the 8 and the 3 to other numbers, you can basically maneuver the chromatic roots anywhere you want on the complex plane. Well, not quite anywhere, but arbitrarily close to anywhere that you want in the complex plane. This also, of course, includes, these graphs are planar, as you can easily see. And so basically there is no restriction at all on the location of complex roots in the complex chromatic roots. Okay. The maximum degree of a graph is an important parameter. So that's the maximum degree. And in a sort of, these two papers by Sokal were in like year 2000 and year 2001. And they solved two of the sort of longest standing problems in chromatic polynomials. And what Alan proved, so this was the first result was the one where chromatic roots could go anywhere. And the second one was a result that showed that the location of the chromatic roots is bounded by some function of the maximum degree. And in fact, the function is some number, 7.96, blah, 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 times the maximum degree. Okay, various other authors have reduced this number to something smaller, but it's still nowhere near what the truth is. Luckily, I know the truth. Unfortunately, I can't prove it. So And the truth is quite surprising. The complete bipartite graph, just on like KDD, I claim has a chromatic root of maximum modulus over all graphs of maximum degree D. So if we take sort of K44, then I'm claiming that no other graph with maximum degree 4 has any chromatic root of greater modulus than the modulus of the maximum, than the maximum modulus of the 8 vertex graph K44. Okay, so the maximum occurs very early in your sort of search through the lists of graphs. If we express, so we know the chromatic polynomial of the complete bipartite graph, and Alan Sokol and Jesus Salas have calculated sort of its limiting behavior. And the answer is, in fact, that that number, 7.96, should, in fact, be replaced by 1.597. So, but I've known this for 30 years, and I've presented it probably like 10 talks in different locations around the world, and nobody has been able to prove it. So the pressure's on you guys now. Okay. But in fact, we don't like the maximum degree anyway, because the maximum degree behaves in a nasty way with regards to chromatic roots. If I take a graph with sort of a vertex of high degree, and then I glue another graph on just at that single vertex, and then another, well, now I'm increasing the degree of that central vertex dramatically, but the chromatic roots don't move at all, because the chromatic roots of two graphs that overlap in a single vertex are essentially the chromatic roots, the union of the chromatic roots of the two graphs. Okay, so having something that's sort of high degree, but like on its own, doesn't really cause us any, doesn't make the chromatic roots go up. So what Alan Sokol and I have looked at is this parameter, lambda, and it's the maximum. So take any two vertices in the graph, X and Y, and now pretend this is a network flow problem and calculate the maximum flow from X to Y, assuming all of the edges have unit capacity. So in other words, it's just the number of edge disjoint paths between X and Y. And what we believe is that this parameter, or a function of this parameter, bounds the location of the complex chromatic roots of a graph. So what this parameter really does is it sort of focuses on a dense local area of the graph. And if you add additional like bits of the graph that are sort of dangling off it at cuts of low size, then the maximum flow doesn't increase, doesn't change. Okay, so that's the conjecture is that there is some bound, is some function of this parameter lambda. And Alan and I proved it, but only for the case of series parallel graphs. And we showed that we take lambda minus 1, divide by log 2, and then all the chromatic roots of a series parallel graph must lie in the disk of this radius centered at the point 1. Okay, so this we'd like to improve. Okay, so those sort of considerations apply to all of the all roots. So let's consider the real roots now. So it was Berkoff and Lewis who first considered taking real values and substituting them into the chromatic polynomial. And the key theorem is that if G is planar, then the chromatic polynomial is positive for all values, all real values of X, at least 5. So that's sort of like the 5-color theorem extended to real values. The Berkoff-Lewis conjecture, they conjectured in addition that if G is planar, then the interval for infinity is free of chromatic roots. And this was the very first conjecture in chromatic polynomials. And it was, well, it's now 75 years old. And as far as I know, nobody has the faintest clue how to solve it. Okay, the motivation for Berkoff and Lewis was, again, the four-color theorem. He wanted to show that there was some interval, real interval around 4 that was free of chromatic roots. Well, then you've proved the four-color theorem. Okay, so let's look at bounds on real roots. Now, this one is just the so-called bound again. It depends on the maximum degree. What about the chromatic number as a possible parameter for the right-hand side? I mean, it sort of makes sense. If you have, say, a bipartite graph, then it has that has integer zeros at 0, 1. And then at 2, it doesn't have a chromatic root. At 3, well, there are more 3 colorings. So it's increasingly, takes increasingly large values, escalating rapidly for each of the integer roots. It would be pretty weird if it suddenly dropped back negative again, and then positive for the next, in time for the next integer. Of course, that's exactly what it does do. And so this is the chromatic polynomial of K814. It has a root at 0. It takes the value 2 at when Q is 2, and then it's positive at 3 and at 4 and at 5 and so on. But in order to do that, it has to sort of zoom down very far negative, zoom up again in time for 3, and create a root at that location. So the real roots are not bounded in terms of any function of the chromatic number, because chromatic number 2 still allows you to have real roots arbitrarily large. Okay. Improvements on the bound. Well, Fengming Dong is a friend of mine from Singapore, and his supervisor, his PhD supervisor was Koki Meng. I put a little Canadian flag there because I'm putting little flags next to people who have some connection with Waterloo or Canada, and Koki Meng did his PhD in Manitoba. Okay, so they basically did Sokol's proof, but did it for the real numbers, simplifying it where you can. And they reduced the constant, the multiplier, to 5.664. Well, that's still hopelessly wrong. Pretty much any conjecture you make about the location of real chromatic roots is feasible, but not proved. So 2 of Sokol's conjectures and others, if you just take any number that is less than the maximum degree, then you should be, so any real number less than the maximum degree, the chromatic number, you can only have chromatic roots for numbers that are less than or equal to the maximum degree. And if you replace that maximum degree with this lambda parameter, then the same conjecture holds. And so the sort of situation for bounding of real roots is quite unsatisfactory. We just don't have, we have essentially nothing except the bound for complex chromatic roots. Okay, so here's the Waterloo's crest. So anyone whose name has a Waterloo crest on it is connected to Waterloo by being either working at Waterloo or having a PhD from Waterloo. Okay, so Bill Jackson was a student of Bondi, and he showed that there are no chromatic roots, real chromatic roots, in the following regions. So let me draw a number line, 0, 1, 32 over 27, 2. So he showed that there are no chromatic roots. Well, you can have a chromatic root at 0. You must have a chromatic root at 1 normally, and up to 32 over 27. Cast and Thomason filled in the rest and showed that there are real chromatic roots dense everywhere onwards. So you've got chromatic roots for a long time, and then you've got as many as you want. Okay, so I'm going to tell 2 stories now. 2 stories, I'll have to be quick though. Chromatic roots near 2. So this is one of the things that I've worked on over several years. Here's a little problem. If G is connected, then 0 is a simple chromatic root. That's easy to show. If G is 2 connected, then 1 is a simple chromatic root. That's also easy to show. What I want to say is if G is 3 connected, then 2 is a simple chromatic root. But that's not true. So here's a 3 connected graph that has a chromatic root of, at 2, of multiplicity 2. Okay, so, but on the other hand, there are classes of graphs which this statement, the strongest statement, is actually true. And I want to know what that class of graphs is. So if G is 3 connected and, well, some condition, then 2 is a simple chromatic root. Unfortunately, to do that, we need to understand the chromatic roots in the interval 1, 2, because you can't have any chromatic roots in the interval 0, 1, so things don't get messed up. But unfortunately, there are chromatic roots between 1 and 2, and that causes us some problems. Any 3 connected bipartite graph on an odd number of vertices will have a chromatic root in 1, 2, because the chromatic polynomial must be heading down as it passes through 1. And it must take the value 2 at the number of 2 colorings of a bipartite graph is 2. And so that means that just to the left of 2 somewhere, there must be a chromatic root. It must pass through the x-axis. Okay, which graphs don't have chromatic roots in 1, 2? Well, Bill Jackson said 3 connected non-bipartite graphs. So he just basically said, we know these do, let's take the ones that don't. We know that these ones do, and let's conjecture that anything without this property doesn't. Carsten Thomason, graphs for the Hamilton cycle. He showed, well, he conjectured this. Okay, Jackson's conjecture is false. So there are counterexamples to the conjecture. There's an infinite family. You just make S and T larger, but odd always. They don't hurt Carsten's conjecture, though, because they are not Hamiltonian. So what's the right condition? What is this condition that's going to make that statement true? Ideally, I want something that obviously excludes the graphs that we know have chromatic roots in 1, 2. And here's the condition that I think is close to the right one. So I'm going to call a graph 1 tough if whenever you take away S vertices, you have at most S components left over. So you can't, so the graph is tough means it doesn't fall to pieces very easily. You can't remove a small number of things and have lots of components left over. Bipartite graphs of odd order are not 1 tough. Every counterexample to Jackson's conjecture is not 1 tough. So my conjecture, or actually this was with Fengming Dong and co, a 3 connected 1 tough graph has no chromatic roots in 1, 2. But somehow 1 tough is not the right condition for an induction. So I can't make it work inductively. Fengming is a master of sort of complex inductions, and he can't make it work. And of course, Carsten is the ultimate master in complex inductions, and he can't make it work either, though maybe he hasn't actually tried with this condition. What happens at 2? Well, Daniel Harvey and I found some graphs with a chromatic root at 2 of arbitrarily high multiplicity. And there's the family, and that was fairly recent, and that was quite tedious to prove because we had to find the chromatic polynomial of this graph and then see what happens as you let the number of those little triangle shapes tend to infinity. But these are not 1 tough either. And there are thousands of other 3 connected graphs with multiple chromatic roots at 2. I mean, I know thousands more. None of them are 1 tough.
Mommy very loves.
So basically, one toughness or some condition like that has a major role to play for chromatic roots in the interval 1, 2, and at the point q equals 2. So that's really what I want to, so that's one strand of the chromatic root story that I have sort of returned to on several occasions. Okay, let's look at the second story I want to tell you, and that's about chromatic roots, real chromatic roots of planar graphs. And I want to look at this region near 5 plus 2, and that's the golden ratio. Okay, so this takes us way back to Tut. So there's a picture of Tut. Obviously, he worked at Waterloo, so he has the Waterloo badge next to his name. This sort of takes me back a long way, because once, like maybe 25 years ago, I was in Waterloo giving a seminar on chromatic roots, and who should turn up but Tut himself. And I immediately fell to pieces because I was so overawed, but he was very polite. Okay, what did he show? He showed that if you take a triangulation, because at this point, they were only really interested in chromatic polynomials of planar graphs, because the four-color theorem was everything. And he showed that he proved this relationship, that the chromatic polynomial evaluated at the point 5 plus 2 is equal to some constant times the chromatic polynomial at 5 plus 1 squared. Okay, and that's an amazing result. I mean, how would you ever like guess that, figure that out? And as this is a little quote from his selected works, which is those little two little books of his selected works with a little description, little sort of commentary before each paper written by Tut himself. And he says, sometimes people find it difficult to believe at first. So, and one of the people who found it difficult to believe was Dickwick Hall. So, so I like to look up people who are involved in these things, so I have some sense of how everything developed. So Dickwick Hall is actually the son of the humorist Dickwick Hall, and Dickwick Hall was not at all his real name. He just adopted that name for some unknown reason. Okay, let's zoom forward now. So Thomas Perrett, well, we know that, why did I say tau? That should be theta. How many times can you read a talk and not find mistakes in it? It's not the chromatic number of any graph, planar or otherwise. And so that means that this number is always non-zero. And when you square it, that means that number is always positive. So, so for any planar triangulation, if you evaluate it at 5 plus 2, then you get some positive number. So the chromatic polynomial of a planar graph will always hop up above the y-axis, above the x-axis for 5 plus 2, and then maybe, well, who knows what it does from there. Okay, Thomas Perrett, a student of Carsten's, looked at this in much more depth in his thesis, and they proved some very interesting results. Unfortunately, Thomas decided to leave academia after he finished his PhD. I was hoping to attract him here, but that didn't work. But I just wanted to check up that he was still doing, you know, I needed to check what I'm telling you. So I looked him up yesterday, and I suspect that he still has some affection for chromatic roots. That's his LinkedIn page. So that looks very much like a picture of chromatic roots to me. Anyway, they showed a beautiful result, which is that if you can find a planar graph, okay, so planar graph, we're going to plot its chromatic polynomial. You know, it'll do its usual thing. If you can find a region where it's negative, an interval of the real line where the chromatic polynomial is negative, then you can basically fill in that region with the chromatic roots of other graphs constructed from your planar graph. So the key thing is that negativity implies density. So all you have to do is find one planar graph with a negative that is negative over a certain interval, and their theorem guarantees you that you can fill in the whole interval as densely as you want with chromatic roots. Well, here's one. I just picked a random planar graph. I did its chromatic polynomial, and look, it's negative over this entire range here. Well, here's 5 plus 2. So that means that just that one graph shows me that real chromatic roots, real planar chromatic roots, are dense in that interval here. Okay, easy. All we have to do now is find a bunch of graphs whose intervals of negativity cover the interval 3, 4, and that will be the strongest possible result that we can get. So that's what we're aiming for. We're aiming to show that planar chromatic roots are dense across the entire interval 3, 4. Of course, at 4, you have the 4-color theorem, so there's no roots there. From 4 to 5, you have the conjecture by Berkoff and Lewis. We think there are no roots there. And then for 5 onwards, we have Berkoff and Lewis's generalization of the 5-color theorem. Okay, 2 exceptions, 2 problems. There are 2 places where we just can't find a chromatic polynomial that is negative. Well, one of them we know about, that's 4. So in here, there's potentially a gap where we don't know any graphs with chromatic roots in that little gap. And then between a little bit to the left of 5 plus 2 and a little bit to the right is also there's a gap there. This is a gap as in when Perrott and Thomason were doing their work. So they found graphs that covered all of the green shaded regions and had those gaps left over. Okay, well, the gap at q equals 4 is not a problem because here's a section of triangular lattice. I want you to think of this as a cylinder, which is sort of going to be growing longer and longer as we're going to add layer on layer of new vertices. It's a planar graph. It's not a triangulation because it has a face at the top, which is a 4 face, and one at the bottom. Well, a few years ago, I showed that if you inserted a certain graph in the top face and a different graph in the bottom face, then you could push some of those complex roots onto the real line. And that gave an infinite family of graphs with real chromatic roots arbitrarily close to 4. Okay, so 4 is done. So now this is what we're left with. Perrott and Thomason found graphs covering almost all of the remaining interval. So this is sort of one family of graphs was negative in that green region there. Another family of graphs was negative in that green region there, so therefore dense. But they couldn't push these points right up to 5 plus 2. They were pretty close though. They were only, these 2 points are only that far apart. Okay, but it's sort of not really satisfactory to say, you know, real chromatic roots of planar graphs are dense in almost all of the interval 3, 4, except for this little range of 0.003246. Okay, so I thought, well, let's just do the same thing that we did with chromatic roots at 4. We'll take a lattice graph, and then we'll bung some end graphs into it, and we'll hope for the best. Okay, so I did this with Melissa Lee a few years ago. Melissa has just completed her PhD with Martin Liebeck. She's doing a postdoc in the University of Auckland, but due to COVID, she's actually physically present in Perth. So, so it's sort of the modern academic is simultaneously everywhere in the world. Okay, so this is my lattice. It's got width 5, and then it's got layers, the family increases in size by adding additional layers. And we're always going to be thinking, what do we do when this number of layers gets very large? Okay. Well, I'm going to skip a lot of details here and just observe that there's sort of general theory that says that the chromatic polynomial of any of these lattices with n layers of repeating structure has this form. You've got a vector that indicates what's happening at the inside or at the top, another vector indicating what's happening at the other end, and you've got a matrix which encodes the effect of multiplying, of inserting another layer. And normally we just let n tend to infinity and see what happens. Okay, these are all, U, T, and V are all vectors / matrices with whose entries are polynomials in Q. Okay. Hard to see what that actually means, so I'll do a little example. So here's the 5p cross nf lattice. So that's the graph that Melissa and I were looking at. This is what U transpose looks like. It's got some multiple, and then it's a vector of length 2 with this as its polynomial, as its first component, and this is its second component. We have a 2 by 2 matrix as a transfer matrix. If I add a single vertex on the inside 5 face, so I insert an n graph, then it changes what V is. And V changes from 1, 0 to Q minus 5, 1. Okay, no problem. Why does that help us? Well, what happens is that certain things become identically 0 when you do some of these changes, and that's really what we're looking for. Okay. If you're taking a matrix to a high power, then, as I tell my first year linear algebra students, you immediately look at eigenvectors and eigenvalues. Okay, so the matrix T, even though it's got entries that are polynomials in Q, you can still often calculate its eigenvalues and eigenvectors, and then you can get an expression for the resulting chromatic polynomial that looks like this. Okay, so alpha 1 is some function called the amplitude. Lambda 1 is one of the eigenvalues of T. In this case, T was only a 2 by 2 matrix, so we've got only 2 eigenvalues. Now, what happens when n gets very large? Well, obviously, the dominant eigenvector, the dominant eigenvalue rather, will win. Okay, so all we need to sort of understand to figure out how this behaves in the long term is to understand these alphas and lambdas. Okay, well, here they are in this particular case. So this is the width 5 thing. I've simplified alpha 1. You should have seen it before it was simplified. And this is lambda 1. Okay, it looks pretty horrible, but it's actually fairly easy for Mathematica to manipulate. And what we discover is that the amplitude of the leading eigenvalue, so the multiplier of the leading eigenvalue, it's negative if Q is slightly smaller than 5 plus 2, 0 at 5 plus 2, and positive at when Q is slightly larger than 5 plus 2. Okay, so if I've got a negative multiple of lambda 1 to the n minus 1, and lambda 1 is the leading eigenvalue, then if I take n very large, then this value will necessarily become negative. So, that means that we can definitely find chromatic roots of planar graphs that are in, or we can definitely find negative intervals for this particular planar graph as close as we want to 5 plus 2 on the left-hand side. Okay, and so that's what one of the chromatic polynomials looks like. Here is the end graph that I have added, just this little vertex of degree 5 in the middle, and I've plotted its chromatic polynomial, and that's what it looks like. Okay. Now, if you don't have that end graph there, it doesn't work. You just don't get any roots in that region. so these n graphs are really crucial to how things work. Okay. Unfortunately, that thing only works for values of q to the left of 5 plus 2, but I also need to fill in that gap from the right-hand side. Well, what shall I try? I mean, I can't just try, I mean, I just went from 4 to 5 and miraculously things worked, but I can't expect that to always work. But luckily, Jesper, Jesus, and Alan have published a large number of papers calculating the zeros for a large number of lattices with different widths and different end conditions and so on and so forth. Okay, each of these papers is a generous 100 pages long or so, so they're not exactly light reading, but if you're desperate, then you have no choice. So on page 26, I found the following table. So that's the real zeros of all of these lattices of different lengths and widths. Probably doesn't mean much to you there, but look what we see here. We see, these numbers look very much like numbers that are just bigger than 5 plus 2. So maybe this lattice will work. Now this turns out to be one of width 10. So now we're looking at a lattice of width 10, and we're going to find some n graphs to put into the ends of it. These n graphs are going to be some triangulation of the 10 gone, and so on and so forth. But there's the graph. There's one of the small ones. Unfortunately, the size of the transfer matrix depends on basically the number of partitions of the interface between one layer and the next. And this one is a 51 by 51 transfer matrix. So that's hideous. Everything works beautifully as long as you're willing to be numerical, because I can calculate the exact chromatic polynomials, because taking a high power of a 51 by 51 matrix is easy to Mathematica. Everything is done in like rational arithmetic or symbolic values. And so these are the left-hand edge and the right-hand edge of the interval of negativity that occurs just after 5 plus 2. So we have 5 plus 2, then the polynomial is always positive at 5 plus 2. For these graphs, it zooms down and then zooms back up again. And this is the left-hand. This is the left-hand side, and this is the right-hand side. Now, are you convinced that these numbers are, that number is tending towards 5 plus 2? I mean, it's exactly 5 plus 2 to that many decimal places. If I do it to 1,000 decimal places, it's exactly 5 plus 2 and so on. So surely that's done. But I can't prove it. So when you take Q to be 5 plus 2 exactly, things simplify a lot. You can work with the matrix, you can work out its eigenstructure and so on. When you try and add a little bit, like mimicking what I did before with the roots at Q equals 4, then you just can't do anything. So maybe we can do something with perturbation theory, which talks about what happens if you make a small change to a matrix. And you know the eigenstructure of the matrix T. Can you say anything about the eigenstructure of the perturbed matrix? And if you're in luck, everything changes continuously and you're happy. So there's a very famous book by someone called Cato, which is very hard to read for someone with my background. But as far as I can tell, if only T had simple eigenvalues, then continuity would work. But unfortunately, T doesn't have simple eigenvalues. It's got some eigenspaces of higher multiplicity. So, this is sort of, this result, I guess, has been on the back burner since, well, for quite a few years. When I was last in Waterloo in 2017, Jim Geelan was sufficiently moved by this result that he announced at the dinner that it had been proved by Dylan Mayhew that there were chromatic roots complex in the region 3, 4. So, so Dylan got some credit that he was not really expecting. Okay, so just a summary, this is my last slide. I strongly believe that chromatic roots of planar graphs are dense in this region. So all of the results combined of everybody, Thomason and so on and so forth. But I just can't prove that tiny little gap above 5+2. So I put it away for a while and then I will come back to it again. So sort of now is what I'm coming back to it again, motivated by giving this talk. And so I'll try and have another crack, maybe find another lattice or find some n-graphs or do something. And then the combination of that would mean that 5+2 and 4 are numbers where the chromatic polynomial of every planar graph is positive, which is sort of a slightly weird result. Okay, the only thing left then is actually the very first thing that I started to work on way back in 1988, which is the Berkoff-Lewis conjecture. So at 75 years old, it started the entire field of real chromatic roots, and no one has been able to solve it. So intense efforts by brilliant researchers, Sokol, Thomason, and so on, not to mention Tut, et cetera, vast computations. The problem just seems to be intractable. No one has any clue, as far as I know, about how to tackle this. Okay. So thank you for turning out. I guess it's close to 7 o'clock for you. It's close to 8 a.m. in the morning for me here. We're in the middle of summer, so we're expecting a sunny day with 38 degrees as our weather forecast. Sadly, I have 3 hours of lectures to give today. Okay, thank you.
Thank you very much. Let's thank Gordon. Wonderful. All right. Are there questions for Gordon before we send him off to start his day?
Might be an easy one, Gordon. Is there an easy proof that there are no negative integer roots?
No negative.
Negative integer roots. You said that follows from.
Oh yeah, it's just because it's alternating coefficients. So you're always adding things. Each term gives you something of the same sign. So Megan asked, do we know the chromatic polynomial of the generalized Peterson graphs? That's a good question. I think some of them are known, but some of them are not. So, but I'd have to look that up.